Hello and welcome. In this course, we will cover several important topics focused on fuzzing, a powerful technique for finding security vulnerabilities in software systems. In this slide, you can see an overview of the contents that are covered in this course. First, we start with an introduction on fuzzing, where we'll explore the goals and we propose some examples of how fuzzing is used to discover vulnerabilities in applications. Next, we will walk through the fuzzing process, explaining how fuzzing works from input generation to vulnerability detection. We will then dive into AFL++, a popular fuzzing tool. We will take a closer look at its key features and why it's considered one of the most effective fuzzing tools available. After that, we will cover some advanced topics in AFL++, such as optimization techniques and how to extend the tool for more complex scenarios. Through the course, there will be many hands-on exercises, giving you the opportunity to apply what you learned. Some of these exercises will involve real-world vulnerabilities, helping you to understand how fuzzing uncovers critical flaws in actual software. By the end of this course, you will have a comprehensive understanding of fuzzing and how to use AFL++ to find and identify vulnerabilities in actual software. So, what are the key concepts behind fuzzing? In this slide, I reported the Wikipedia definition for fuzzing, but let's focus on the keywords. The first keyword is automated. Fuzzing is an automated process, meaning that once the initial setup is complete, no human intervention is needed to generate inputs or to run the tests. Let's say more or less no human intervention. The second keywords are invalid, unexpected, or random input, because in fuzzing, we intentionally feed to the target system inputs that are either malformed, unexpected, or completely random. These inputs deviate from what the system will normally expect, with the goal of uncovering vulnerabilities that arise from unusual or edge case scenarios. The last one is monitoring for exceptions. Fuzzing involves monitoring the system for any anomalies or errors, such as crashes, memory leaks, or unexpected behavior. The aim is to catch these issues as they occur during the test, helping to identify potential weakness in the system. So, we can say that the primary goal of fuzzing is to uncover issues that can compromise the stability and security of a system. Let's break it down some of the key outcomes we are trying to identify. The first one is security vulnerabilities and bugs. Fuzzing helps to identify hidden security flaws that could be exploited by attackers, such as buffer overflow, memory corruption, or improper input handling. Then we have the crashes, because by fitting unexpected or invalid inputs to the system, fuzzing might trigger crashes, which indicates potential weakness in how the system handles error conditions. Then we have unexpected behavior. Fuzzing also helps to detect behaviors that fall outside the normal operational parameters, things like logic errors, data corruption, or situations where the system does not respond as intended. These issues might not cause immediate crashes, but they could lead to unpredictable results or degradation of the service over time. Okay, so now let's have a look to some examples. In the first example, we consider web application fuzzing. In that case, we target a web application with a directory discovery attack, sending multiple requests to find hidden directories or URLs. So, what we are testing? We are checking if the server exposes sensitive resources, like admin pages or private files that should be restricted. The outcome is that if successfully, we might find exposed resources, indicating a misconfiguration or a lack of access control. In the second example, we consider file format fuzzing. In that case, we test, for example, a PDF reader by sending to it corrupted or malicious PDF files to see how it reacts. So, what we are testing? We are checking if the reader properly validates files before opening them. And the outcome is that the reader crashes. It could reveal a vulnerability that attackers might exploit to run malicious code. Finally, in the last example, we consider network protocol fuzzing. In that case, we send broken packets to a server using a specific protocol. We are testing how the server deals with unexpected or corrupted data. And the outcome is that if the server crashes, it could indicate vulnerabilities that attackers could exploit to gain control of the server. So, fuzzing helps to find hidden vulnerabilities by sending unexpected or malformed data. This can uncover security flaws and stability issues that regular testing might miss. Now, I would like to focus on three main categories of fuzzing. First, we have mutation-based fuzzing. This method starts with a set of valid inputs, often called seeds, and generates or mutates them to create new test cases. The mutation can be simple, like flipping bits in the input or removing, altering, or adding parts of the input. Mutation-based fuzzing is easy to set up if you already have a good set of inputs. It's great for finding edge cases or bugs that are close to the original inputs. However, it has some limitations. It can only work with the variety and quality of the starting inputs, and it might miss bugs that need very specific or unusual inputs. Next, we have generation-based fuzzing. This method generates and creates test inputs from scratch, following specific rules or structures. Unlike mutation-based fuzzing, it doesn't rely on existing valid inputs. Instead, it generates new inputs that fit a given protocol or data format. For example, it might create network packets or design inputs for a specific file type. Generation-based fuzzing can test a wider range of inputs, including rare or unusual ones. It is especially useful for testing protocols, file formats, or complex systems with well-defined rules. The con is that it requires more knowledge of the input format, and it's harder to set up than a mutation-based fuzzing. Finally, let's discuss coverage-guided fuzzing. This is a more intelligent approach because it uses feedback from the program's code coverage during execution. After running an initial set of inputs, the fuzzer looks at which part of the code are executed, and based on this information, it generates new inputs to explore part of the code that have not been tested yet. The main strength of coverage-guided fuzzing is that it focuses on maximizing the code coverage, helping to find bugs that might be hidden deep in the program. It's very effective for finding complex bugs that other methods might miss. However, it can be more complex and slower because it requires continuous monitoring and analysis. It also depends on having the program's code instrumented, which is not always possible. So, to summarize, mutation-based fuzzing changes existing inputs, but it might test the same code path too many times. Generation-based fuzzing creates inputs from scratch, but it doesn't adjust based on how much of the code has been tested. Coverage-guided fuzzing combines the best of the both, using feedback to test new parts of the code and find harder-to-find bugs. Now, let's compare fuzzing with static and dynamic analysis. Both methods are useful, but each has its own strengths and limitations. Static and dynamic analysis are great for small code base. Static analysis reviews the code from issues like security flow, while dynamic analysis monitors the application during the execution. However, both require deep knowledge of the system and can be time-consuming, especially for large or complex applications. While some parts can be automated, human input is still needed for setup and interpretation. Fuzzing, on the other hand, is ideal for complex or large systems. It doesn't require detailed knowledge of the code. Fuzzing tools automatically generate inputs and check for crashes or unexpected behavior, making it faster and more scalable. It is also fully automated, needing little or no human involvement once set up. In summary, static and dynamic analysis are best for small code bases and require more manual effort, while fuzzing is better for complex systems and large applications, as it is fully automated and faster. Combining both methods can provide the most true coverage. To continue, let's now look at the differences between white box and black box fuzzing. White box fuzzing requires access to the source code, which allows for better code coverage and makes it easier to find hidden bugs. By understanding the internal structure, we can create more effective and targeted test cases. In contrast, black box fuzzing does not require knowledge of the source code. It tests the application from an external perspective, simulating real-world user interaction or how an attacker may use the system. This is really useful when we don't have access to the source code. There is also a middle ground approach that combines elements of both, taking advantage of the strengths and weakness of each method. We call it everything in the middle. In this course, we will focus more on the white box approach, as we will be fuzzing open source projects with full access to the source code. In the real world, both approaches have their strength and are useful in different situations. Understanding these differences helps us to choose the right fuzzing strategy for our specific testing needs. Now, it's time to talk about the generic fuzzer. We can say that usually a fuzzer is generic because it doesn't matter what we want to fuzz. In fact, a fuzzer is not dependent on the target. What can be is that a fuzzer is specific or more suitable for some specific architectural languages. The best way to explain this concept is with an example. In this example, we will fuzz an MP3 player. We start with a normal file called coolmusic.mp3, and the MP3 player application. Since the input file or the initial corpus is an MP3 file, the magic byte sequence is 494423. Next, we validate our seed, which is the initial MP3 file, and test it with the application. So we feed the seed into the MP3 player, and it plays the music. And of course, everyone is dancing. But how does it work behind the scene? The MP3 player has an interface that accepts our seed, the MP3 file, and calls the underlying implementation to decode the file and play the music. But what if the implementation changes? If the implementation changes, the interface will use the new version automatically, without needing to change the fuzzer or the initial seed. And this is where the harness comes in. So, to be able to fuzz our target without worrying about the implementation, we have to build the harness. The harness is like a boilerplate code that passes the input from the fuzzer to the functions we want to test. It helps us to avoid worrying about the underlying implementation, and we don't need to manually interact with the system. Especially, it is really useful in UA-based software. Once the harness is set up, the fuzzer generates new inputs starting from the initial set of examples, the corpus, and passes them to the harness. But how do we create new inputs? We need to mutate the initial corpus. However, not all mutations are useful. For example, in the picture, we can see that the mutation number 2.mp3 file has a different magic bytes, which make it unplayable. As a result, the player simply rejects it. In the next video, we will explore mutation fuzzing process in more detail.